Welcome to this final video about the reactions of alcohols. Hopefully by now you should be clear and understand the oxidation reactions of alcohols using acidified potassium dichromate. The purpose of this video is to look at two further reactions: elimination to form alkenes and substitution reactions to form haloalkanes. The final reaction, esterification, is a topic which is covered in Year 13 and won't be covered in this video. So let's begin with elimination. Sometimes the elimination reaction is called a dehydration reaction because an alcohol can be dehydrated to form an alkene in the presence of an acid catalyst. What's going on in this reaction is the OH group is removed from one carbon and a hydrogen is removed from an adjacent carbon atom to form water. A carbon-carbon double bond is also formed. Typically, the catalyst for these reactions is either concentrated sulfuric acid, H2SO4, or concentrated phosphoric acid, H3PO4. Let's look at some worked examples. These are both pretty straightforward. Ethanol can be converted into ethene. What occurs in this reaction is the removal of the OH group from one carbon atom and a hydrogen from an adjacent carbon atom. This means we can form a carbon-carbon double bond between these two carbons. The rest of the molecule remains unchanged. And we also form water. As we've said, for this reaction to occur, you need a concentrated acid catalyst. Similarly, if we started with cyclohexanol, although it may look more complex, the reaction is the same. We're going to remove a OH group from one carbon atom, and then we're going to remove hydrogens from adjacent carbon atoms. So, in this case, we would form cyclohexene and water. It doesn't matter in this case whether I took hydrogens from this side or from this side. I'd still form cyclohexene. A more complicated example would be to use an alcohol such as butantuol. In butantuol, we could remove an OH group and a hydrogen from an adjacent carbon atom. If this occurred, we would form a carbon-carbon double bond between carbons 1 and 2. The rest of the molecule would remain unchanged. Now, something to remember and to link to previous topics is that when we have a carbon-carbon double bond, we need to start thinking about stereoisomerism. In particular, EZ isomerism. For there to be an EZ isomer, we're looking for a carbon-carbon double bond, and for each carbon atom to have two different groups attached to it. In this case, there is going to be no EZ isomerism, because one of the carbons has two identical atoms attached. However, going back to our original butantuol, if I remove the OH group from this and a hydrogen from this carbon atom, what I now get is a carbon-carbon double bond between carbon 2 and carbon 3. And in this case, I can see I've now got a carbon-carbon double bond present, and each carbon atom has two different groups attached to it. Pause the video and think, is this the E or Z isomer? Is this the cis or trans isomer? And when would I use the terminology cis and trans? Okay. In order to decide whether something's E or Z, I need to give priorities to groups. And in this case, I'm going to give priority to the carbons over the hydrogens. So I can see I have got this molecule. It's but2e, but the two priority groups are not diagonally opposite across the double bond. If I'd gone back to my original butan 2-ol and instead of removing this hydrogen, I had removed this hydrogen, what I would now have would be this molecule. This would be the E isomer. Z isomer, E isomer. The E isomer because the priority groups, the CH3 and the CH3, are diagonally opposite across the double bond. So when I do an elimination reaction from something like butan 2-ol, I need to consider stereoisomers and structural isomers. The great thing about this topic is we're making links between the alcohol topic, the alkene topic, and also we're making links into the ideas about stereoisomerism. Really, really important when it comes to exam questions. NB. Take note. Note well. Here's a little bit of cultural capital for today's lesson. So just to recap, because this is really important. Taking an alcohol and doing an elimination reaction, you need to think about the variety of products that could be formed. Consider, do we have structural isomers and do we have stereoisomers? It's often one of the stereoisomers that people forget to draw in such an answer. The final part of today's lesson is about substitution reactions, turning an alcohol into a haloalkane. This is one of those little parts of the syllabus that oftentimes by the time that people get into year 13, they've kind of forgotten, but it does come up, often as a 1-mark question. Turning an alcohol into a haloalkane. You need to use halide ions, usually provided by something like sodium bromide, in the presence of a concentrated acid, like concentrated sulfuric acid. And when you have sodium bromide and concentrated sulfuric acid, the OH group is replaced by, in this case, the bromine atom. This is a substitution reaction, a swapping. In this particular example, we've gone from propan 1-ol to 1-bromopropane. That's the end of this video.